Oh.
All right, how's everybody doing? Should we get started? Maybe not. Just go home. All right. We don't have a whole lot to do today, actually. So, if you've got questions and stuff, this would be a good day for that. We're going to finish up talking about gases. We're not going to have a quiz next week because this chapter doesn't have a whole lot in it. We will wait another week and do the quiz on the Monday or on the Tuesday. I guess that doesn't make sense because of the exam.
Wait, when is the exam?
The exam is a week from Tuesday. So we'll probably do the quiz on Thursday after the exam. So the exam will be on Tuesday, we'll do the quiz on Thursday. Because it doesn't really make sense to do quiz on Tuesday and then do the exam an hour later. So, does that sound good? All right.
Yeah.
So in 2 weeks from Thursday will be the quiz. The next quiz. Quiz 5. Okay. All right. So all we have really left to do is talk about the different relationships that we saw in lab on Tuesday, and kind of put them into a form that makes sense, and talk about where they came from a little bit. And then we're going to look at the theory behind it and see how we can explain these effects that we see. So let's first look at the relationship between pressure and volume. What is the relationship between pressure and volume, and which of the demonstrations on Tuesday showed that? Anybody remember? What? Balloons. Well, that narrows it down a little. Which balloons? What? And that showed a difference between pressure and volume? How? So the nitrogen changed the pressure? So which one showed a difference between pressure, or a relationship between pressure and volume? Yeah, the one with the vacuum, right? So that we had this kind of container with this bell jar over the top of it. And there were some balloons in there, and there was one like hanging from the top. And then as we evacuated the container, what happened to the balloons? Yeah, the balloons expanded. So we evacuated the container, took all the air out, and then we had the balloons got much bigger. I don't know if they really got that much bigger, but they got bigger. So that showed that this was an example of higher pressure, and this was lower pressure. So what can we say happens to the volume when the pressure is decreased? Volume increases, right? This is known as Boyle's law. Boyle's law of gases. And it just says there's an inverse relationship between pressure and volume. When one goes up, the other one goes down. When one goes down, the other one goes up. That's what an inverse relationship means. One goes down, the other goes up. The way we can think about that mathematically is often written like this. We're not going to worry about solving specific problems for these quantities, but the idea being that the product of the pressure and the volume stays constant. So if one goes up, the other one has to go down to compensate. If one goes down, the other one has to go up to compensate. So that's how you could actually solve for numerical values of pressure and volume if one changed. So if we measured the volume of those balloons initially, and we knew the pressure was atmospheric pressure, then the pressure goes down, we could measure the new pressure and calculate the new volume of the balloon based on that. All right, so now let's look at our next relationship, which is temperature and volume. Which demonstration showed a relationship between temperature and volume? When the temperature changed, we saw a change in volume.
When the volume water and ice pad, and then liquid nitrogen.
I think you're kind of mixing some stuff up together there. Think about it again, what the individual effects were and what the apparatus was that we used. Right, so that one, yeah. Get some more space here. So for temperature and volume, what we did was we lowered the temperature of balloons and we saw what happened. How did we lower the temperature of the balloons? Yeah, that was with the liquid nitrogen. So the very cold liquid nitrogen poured on the balloons, which lowered the temperature of the balloons. And what happened to the volume? Yeah, it went down. The balloons got much smaller. And so we had this this pan with a couple balloons in it. And then we poured the very cold nitrogen on top, which is sometimes called LN2. And the temperature of liquid nitrogen is 78 K or 77 K. Close enough, but so very, very cold. Minus 195 C. So it is 78. So we put that very cold liquid nitrogen on there, and then we saw these balloons get very small, very kind of crinkled up. So the cooling, the air inside the balloons caused the volume to shrink. And this is known as Charles' law. The way we say that is that temperature and volume are directly proportional. In other words, if T goes up, then volume goes up also. If temperature goes down, volume goes down. To write that in that same kind of equation way, we could say if you have an initial volume and an initial temperature, and then you have a second volume and a second temperature, meaning you've changed them, they still have to divide the same thing. So if one goes up, the other one has to go up to compensate. If one goes down, the other one has to go down to have the same number. All right, sound good so far? All right, the last one we saw yesterday was the relationship between pressure and temperature. And what was the relationship? What did we see as a relationship between pressure and temperature? What was that one? The what?
Is the ice bed and
Yeah, putting that steel, rigid steel ball that was filled with air at a particular pressure into the different solutions. So we had the sphere, that kind of steel sphere, and it had a gauge on top and a handle. And the needle on the gauge was pretty much pointing straight up. And then when we put it into a really cold room, when we put it into some cold stuff, we saw the pressure go down. So we had the thing with a particular pressure, the volume stayed the same, but as it cooled down, the pressure went down. And then as it heated up, the pressure, when we put it in the boiling water, the pressure went up. So that tells us that the pressure and temperature has that same kind of direct relationship. That a decrease, right, in temperature requires a decrease in pressure. That's another example of a direct relationship. One goes down, the other one goes down. Yeah.
Yesterday, I went to the doctor,
Mhm.
and I told her I had a headache last week, and she told me a lot of people went through that, and the biometric pressure of the ones was changing. That's what she told me.
Okay.
Biometric.
Barometric.
What's
Barometric is the pressure of the atmosphere on the Earth, and that changes depending on the weather. It varies a little bit. Yeah. I think it's over here. Let's see. We can look up some past weather. I don't know if you can find. So when was it? Tuesday?
last week?
Last week sometime? Well, that's temperatures. You can find what? Barometric pressure, yeah. I'm trying to find if we can see if we can find the actual daily summaries from, let's say, what month is this? October, right? So let's say last week, Sunday to Saturday. Around here. They don't have one for pressure, so I don't know how we might find that. We'll see. Anyway, if we look at the weather today, I can show you where you find that. Except everything stopped working right now, so maybe we're not going to find it. Okay, so everything's broken and not working, but that's fine. One more time. but we'll look at it later. But you can look at these weather sites and they'll graph the barometric pressure, which is the pressure of the atmosphere over time, and it changes slightly from day to day based on what's happening in the atmosphere. I'm not sure if the idea that causes headaches or if that's actually been substantiated, or if that's just kind of like a thing that people think. I don't know. I can say one way or the other, but I've definitely heard that before. Yeah. I mean, it certainly makes sense. Like the atmosphere exerts a particular pressure, and if that pressure changes inside our head based on what's pushing on us from outside, that could lead to some effects. I don't know. All right, so that's our 3 relationships. This one, by the way, is known as Gay-Lussac's law. But the important thing you need to know is these relationships. So you need to know what happens when one of them changes. What does the other one do? There's a 4th one that we didn't test in lab, but it's pretty straightforward, and that's known as Avogadro's law. And that is that an increase in the number of moles of gas, or the amount of gas molecules, gives an increase in volume. So if you put more gas in a balloon, it will get bigger. That one's pretty straightforward. Obviously, if you put more gas in the balloon, it's going to get bigger. Similarly with pressure, if you have something that's constant pressure and you put more gas in it, or constant volume, I'm sorry, constant volume, you put more gas in it, the pressure goes up. That makes sense too, right? Put more in there. The thing that's a little bit weird about this is that it tracks with moles of gas, not with the mass of the gas. The reason being that in a gas, and we're going to talk about some of the definitions of what a gas is, but in a gas, the spaces between molecules are so great that the actual space the molecule takes up doesn't really matter. So the number of gas particles is way more important than the size of each gas particle when we're talking about effects like volume and pressure. So for an interesting example of that, let's look at a chemical reaction that would take place inside a balloon. So we fill a balloon with oxygen gas. And this oxygen gas reacts to form ozone gas. Ozone is O3. And the question is, what happens to the volume in the balloon? Now, initially, the kind of like common sense, obvious answer is that nothing happens. But that's not actually true. If you take oxygen gas in a balloon, you convert it to form ozone gas, something's going to change in that balloon. Nothing is leaving the balloon, nothing is entering the balloon. You're simply doing a reaction. And yet you change the volume because you can actually change the number of moles. So we need a balanced equation here. We have oxygen gas, which is O2, becoming ozone gas, which is O3. That's our chemical reaction. Is that balanced? No. How do we balance it? Yeah, we need a 3 here and a 2 here. And now we have a balanced equation, 6 oxygen atoms on each side. So what this equation tells us is for every 3 oxygen molecules, we make 2 ozone molecules. If we draw that, oxygen molecules look like this. There's our 3 oxygen molecules, and they become 2 ozone molecules. Ozone looks like this. So what has changed with our moles of gas? How have our moles of gas changed? in this way. But they've decreased, yeah. We started with whatever amount we started with, we're going to have 2/3 as much of that after the reaction is done in moles. We have the same amount of mass in there, but we've changed the number of actual particles. And because the volume and the pressure depend on the number of gas particles, not on the mass of that gas particle, we would expect the volume to go down. So even though no molecules have escaped or entered the balloon, the volume has decreased because of the reaction, because those atoms are now stuck together in different ways and we have fewer molecules or fewer moles of gas. So that shows what happens when we do this. Now, all of these laws together have shown us what happens. They've shown us, you know, you do this and then this thing happens. And that's why they're all named as laws. Remember the difference between a law and a theory? A law is something that happens, a set of observations, and a theory is the reason behind that. What's causing those things to happen? So in these cases, the laws are just, you know, you change pressure, volume changes too. You change volume, temperature changes too. All that stuff. We need a theory behind it that actually explains why this stuff happens. And so the theory behind it is called, a new page here. It's called the kinetic molecular theory of gases. The kinetic molecular theory is how we explain what's really happening here. So we're going to assume 5 things about gas molecules. And if those assumptions hold true, then we should be able to explain all these different effects that we see. So we'll look at the assumptions, and then we'll use them to explain the things that we see. All right, some of these are more obvious, some of them less so. So first, we're going to assume that gases consist of small particles that move randomly at high speed. So tiny, tiny particles moving really quickly. That's pretty straightforward. Second one, we're going to assume that because they're so small and so far apart, that attractive forces between gas molecules are insignificant. So we don't need to think about how the gas molecules attract each other. We're going to say they don't attract each other. When they hit each other, they simply bounce right off again. They don't transfer any energy, and they're not kind of being held together. So all that stuff about hydrogen bonding and dispersion forces and dipole forces, the stuff we talked about in the last chapter, doesn't really apply to gases because the molecules are so far apart and moving so fast. Third, the actual volume occupied by the gas molecules is tiny compared to the volume the gas occupies. So I have to get that one down. So that means that in any sample of gas, the actual space taken up by the molecules themselves doesn't really matter. It's so tiny compared to the volume of the container that we don't need to worry about the volume of each individual particle. And that's kind of what we talked about just before with this issue of moles, that even if you have not changed your mass, you can still change your space if you have fewer particles, because we don't actually care how big each particle is. It's only the samples themselves. And this is because the space in between gas molecules is so many thousands and millions of times bigger than the size of the molecules themselves that the sizes of the molecules doesn't really matter. All right, and then these last two are what we're really going to use to kind of predict some of these effects that we see. The fourth one doesn't really sound like much until we talk about what it means. I'm going to say gas particles are in constant motion moving rapidly in straight paths. So they never stop. They're always moving, and most importantly, they're always going in straight paths. The reason it's important that they're moving in straight paths is because imagine that I'm standing here and I suddenly take off running in a straight line and don't stop. What's going to happen? I will run into the wall, right? And that's really important, because what comes from this idea then is that the collisions of gas molecules with the container walls is what we call pressure. We didn't really talk about what this pressure idea comes from. We talked about like pressure from a physics standpoint of standing on something or putting a force over a particular area. But what's actually exerting the force on the walls in the sample of gas? We don't really think about that. So we say, well, what's exerting that pressure is the gas molecules colliding with the walls. And if gas molecules are all going in straight paths, eventually they're all going to hit the wall. They're going to bounce off and then go hit another wall. Bounce off, go hit another wall. So the overall pressure in the container is the sum total of all of the collisions of the gas molecules. That means if our molecules are hitting the wall more often, we're going to have higher pressure. If they're hitting it less often, we're going to have lower pressure. So that's this idea of where pressure comes from. It comes from the collisions of these fast-moving molecules traveling in straight lines. And then finally, the average kinetic energy of gas particles, so the average energy that they have, we'll talk about what that means in a minute, is proportional to the Kelvin temperature. Anybody here ever taken physics in high school or anything? What's kinetic energy? you know?
Not
It's close, it's related to that. Kinetic energy, we talked about a little bit, it's this energy of motion when we talked about heat and stuff, but what is it, if we put it into an equation, does anybody know the equation for kinetic energy of something that's moving? Uh-oh. Pretty sure I was not supposed to do that. Is there some tape over there? So what are some variables that kinetic energy depends on? Does it depend on like distance, mass, acceleration, force? What kind of stuff does kinetic energy depend on, you know? Throw some variables out there while I fix this thing. Nobody remembers. Been too long. Position is not quite, but the here I'll put it out in a second. I just have to. This tape is not starting properly, so I can't get my pen going. All right, well, I'll try to write with it and just see how it breaks or down. Kinetic energy is, whoa, yeah, that's not really going to work, is it? We're almost done. Close. That's terrible. We'll put it on the board. Kinetic energy is 1/2 mv squared, where m is mass and v is velocity. So that tells us that the kinetic energy of these gas particles depends both on the mass, that is, how heavy are they, and also how fast they're traveling, the velocity. So that's really important because that's proportional to the Kelvin temperature. We talked about heat, but we didn't really talk about what temperature is as a measure. It's actually a measure of molecular motion. And it's not just about gases, but anything, any molecule, any atom, any particle that's above absolute zero in temperature has some motion associated with it. It's moving. Even if it's not moving through space like a gas molecule, it's vibrating or something like that, like in a solid. So that molecular motion is associated with the temperature, which means that what is happening to a gas molecule or a gas sample if we slow down the molecules? What happens to, according to this, if we cool, well, if we cool them, we're slowing down the molecules. So do you see how that would work? That's why that's a really important idea, that the kinetic energy is proportional. It can also tell us some other things. Since the kinetic energy depends on both mass and velocity, let's say we have two samples of gas. We have neon, which is up near the top there, Ne, and we have xenon, which is Xe, down near the bottom. If you had two samples of gas at the exact same temperature, which atoms are traveling faster? The neon atoms or the xenon atoms? Or are they going the same? They're at the same temperature. Why the neon? Right, so the neon atoms have less mass, which means that they must have a greater velocity because they're both at the same temperature. So they have to have the same overall energy. So if one of them has less mass than the other, it has to have a greater velocity to compensate. So we can say something about how quickly our molecules are traveling based on that. Let's see how I can do with this repair job. Suppose I could just like call the IT and see if I can get a new one of these, but this is kind of fun. Yeah, it works. So now you know that even though I'm quite small, I actually have an incredible amount of power and that I was able to snap this thing in half. All right, you guys enough tape? A few more wraps around in there. Do we need to fix anything while I got the tape out? Yeah. Okay, so let's fix this terrible equation. There's our kinetic energy. So we can say these things about the that we just talked about. All right, so these are all the tenets of the kinetic molecular theory of gases. It may not seem like it, but we can use these ideas to explain what's happening in the laws. And the way we do that is by thinking about things like how temperature affects molecular motion. So rather than just saying, well, temperature is just this thing, and when we increase it, it leads to this, we say, well, temperature speeds up the gases, and faster moving gases are going to do this. And that's the way that we explain what's actually happening. So let's go back up to some of our laws, like this one, kind of the most dramatic one from the demonstration. So we poured liquid nitrogen on balloons, and they shrank up. So here's an example of how to or not to answer a question like this. Let's say I asked you on a quiz or exam, I said, liquid nitrogen gets poured onto some balloons, and the balloons shrivel up. Why did that happen? The wrong answer, it's not wrong, but a not great answer is to say, well, that was because of Charles' law, because temperature and volume are directly related, and when you decrease the temperature, you decrease the volume. The reason that's wrong is it's not a reason. It's just stating the question again. That's essentially me saying, why did the volume go down when we brought the temperature down? And you answering, well, because the volume went down when the temperature went down. It's not really a great way to answer a question if you just restate what the person asking the question is saying, although I've seen some people try. So a better way is to think about it from the molecular level and think, what is actually happening with the individual gas molecules here that's causing this change? So we can say, well, in this case, the temperature going down does what to the gas molecules?
Decrease the
Yeah, slows them down, right? Because of that fifth part of the kinetic molecular theory, we know that the lower temperature means slower moving gas molecules. So if the gas molecules are moving slower, what does that say about the collisions with the walls? Now what?
It's not frequent.
Right, yeah, right, not as frequent. So we're not having as many collisions with the walls. If we imagine, we should try this sometime, but we can take all the desks and kind of get them out of the room, and we'll all just have blindfolds and run, but we stay in the room, and we start hitting the walls. Let's do it. It's a good idea. There's like you guys are all healthcare people, right? We take care of us when we hurt ourselves. So we'd hit the walls, we'd run around hitting the walls. If we run more slowly, which is the decrease in temperature, we would hit the walls less often.
Okay.
Everybody sees that?
It's good pressure. What about volume?
So what about volume? Well, this idea of relationship between temperature and volume tells us that the pressure has to stay constant. So if we're changing temperature and we want to know what happens with volume, we have to hold the pressure constant. The pressure is the collision with the walls. So if we're running more slowly, but we want to hit the walls just as much as we did before, what has to happen to the walls? They have to come in, right? If we had half the size of this room, we could run half as fast and still hit the walls just as much. So that's how we kind of think behind this. Let's think about this next one. This one's probably even more clear. Pressure and temperature. If you heat up the gas, what happens to the pressure? Goes up, and this is at constant volume. So why is that? What's happening to the molecules so that when you heat them, yeah, exactly. So they move faster, which increases the collisions with the walls. And if you've increased the collisions with the walls, that means you've increased the pressure. Right? So if we're all running around blindfolded, we're in the same size room, but we start running faster, we're gonna hit the walls more. We run slower, we're gonna hit the walls less.
Those particles ever hit each other?
Excuse me, yes. Yes, they do. And so one of the assumptions as part of that kinetic molecular theory is that collisions are elastic, which means no energy is transferred when they hit each other. So you hit each other and then you start going in the opposite direction at exactly the same speed that you were at when you hit each other. But yeah, they're hitting each other and the walls. All right, so then finally, last couple then. How do you explain Boyle's law using the kinetic molecular theory? How do you talk about the relationship of pressure and volume when temperature stays constant? Thinking about these ideas of collisions and speed and stuff like that. We want to try to explain that one? Pressure and volume. What do you think? Yeah.
When we decrease pressure, particles are closer, and then the volume decreases. No,
Kind of. What do you mean particles are closer?
the distance between particles. Is short.
But if pressure is defined as collisions with the walls, how is decreasing pressure making particles closer? Or is it?
The volume. We decrease.
Yeah. So I think it's
We have to start with the volume.
right. So I think it makes more sense if you think about the volume
that
first.
Was my question. What is the
Yeah.
first?
Yeah. So we'll talk about thinking about it both ways. But in this case, the temperature is constant, which means everything's going at the same speed. Speed of the molecules is not changing. If we change the volume, if we, let's say, decrease the volume, make the room smaller, how does that affect the collisions of the particles? The increased collisions or decreased collisions? Increase, because you now have a smaller container. So the increased collisions is the higher pressure. So the smaller container, the smaller volume, it leads to a higher pressure. If you want to think about that the other way, you think, well, okay, if we decrease the collisions without changing the speed, then we must have to shrink the walls, shrink the container to decrease those collisions. So it's not so much that the gas particles are becoming closer together. That's the effect of it because they're now in a smaller container. But the cause of it is either the change in collisions or the change in the size, change in volume.
Okay, so this Charles' law,
Mhm.
you talk about temperature and volume,
Right,
but you talk about temperature and pressure.
right.
So what's the connection here between volume and pressure?
Yeah, the key here is that this is always at constant pressure. So the pressure can't change. If you're going to change temperature without changing pressure, then the volume has to change. Or if you're going to change volume without changing pressure, the temperature has to change. So you can say, let's go the other way with it. Let's say we want to decrease the volume. What happens to the temperature? Well, if the room gets smaller, but we got to keep the same number of collisions with the walls, that means we got to go more slowly.
Second one, have the scale over slow.
Mm-hmm.
So it shows pressure and temperature.
Right. So it's a similar idea in both cases. Either you're looking at how the pressure changes, or you're looking at how one changes to require.
And then,
Right.
like temperature is changing, the pressure is constant. And here, like when pressure change, like temperature changes and then pressure changes.
Right.
So we don't have it constant, because if we will change temperature here in Charles' law, then it will decrease also.
Well, that will depend on your system. So you can have a constant pressure system, like a balloon that can change its shape,
Okay.
or you can have a constant volume system where it's fixed. So the pressure and temperature is,
So some
at constant volume.
Okay.
Yes, so whichever two you're looking at, the other thing has to be constant. Similarly, with Boyle's law, with pressure and volume, we have to be at constant temperature. If we want to look at just that relationship. And then the last one, Avogadro's law, we can explain in the same way. If you increase the moles of the gas at constant pressure, then you need a larger room if you want to keep that constant pressure. We can also think about it in terms of pressure. If you increase the moles of gas, but you keep the same size room, you're going to have more collisions. That's a higher pressure. All right. So those are the reasons behind these effects. These are the observations. These are what happens. But if you want to know why something happens, you have to look at what's happening to the molecules themselves.
I have a question about this reaction. Like oxygen gas interacts to form ozone gas, but how it happens? What's the reaction? Like it doesn't change anything.
It's actually a, yeah, the oxygen molecules are reacting with themselves, with each other. So this is caused by energy. Energy gets put in to help them do this, usually UV light or something like that. And some amount of oxygen atoms will do this, or oxygen molecules will do this on their own, but usually this is something that happens either in the presence of light or some other kind of catalyst that helps it along. Any questions about that? Okay, the last part about gases that I want to look at is something called partial pressures. It has to do with measuring gases. The gases can be a little hard to measure. We talked about this a little bit on Tuesday. But when you can't weigh them usually on a regular balance because of their difference in mass with air, it's just complicated that way. You can sometimes measure them in volume, like with a flow meter, but that's usually not really quantitative. The best way to measure gas and make sure you know how much you have is by pressure. The higher the pressure, the more gas you have in a given container. So if you know the pressure and you know the volume of the container and you know the temperature, you can calculate how much gas you have. We're not going to do those calculations in this class, but there is one interesting effect of this, that is gases that are mixed actually exert their own pressure individually on the container, and the total pressure is then the sum of the pressure of each component. So if you think about the kinetic molecular theory, what we just talked about, that kind of makes sense. If the pressure is caused by collisions with the walls, and let's say we have a mixture of helium and oxygen, the helium molecules will be exerting some pressure. The oxygen molecules will be exerting some pressure because they're both colliding with the walls. So they each kind of exert their own pressure, and the total pressure in the container is both of those together, whatever all the molecules are doing together. So that means that if you took like two gas tanks, let's say we've got a little gauge on here. All right, here's our first gas tank, and this is helium. And we've got 2.0 ATMs, 2 atmospheres of helium in that tank. And let's say it's a 20-liter tank. And then we've got another tank another 20-liter tank that has oxygen, 5 atmospheres. So we've got this pressurized tank of helium, 2 atmospheres of pressure, pressurized tank of oxygen, 5 atmospheres of pressure. If we put all that gas together in one same size tank, we can simply add the pressures up. So our total pressure in that container is 7 atmospheres. But then we can talk about 2 partial pressures in that container too. The partial pressure of oxygen is still 5 atmospheres. And the partial pressure of helium is still 2 atmospheres. So each gas, even though they're together, each gas is exerting its own pressure. And so we can talk about the proportion of one or the other based on how much of the total it's adding up to. So let's see, do we have any internet access yet? So I want to show you one thing from the book in this as well. There we go. Okay. So this will be from the book in this part. All right, so it wasn't the internet, it was just that website that's not working. Although now this one doesn't seem so great either. Maybe we'll not be looking at these. All right, here, let's see if I can find this one here. Just all kinds of fun technical difficulties today. Must be something going on with Harper Internet because this thing is on a different network and it's not loading properly either. Okay, well, I will just tell you to refer to your books. There's an interesting table in this chapter that talks about the partial pressures of the different gases in air. So what are the major gases in air? You know? Oxygen, nitrogen, not much helium, not much hydrogen. There's 2 other main ones, but carbon dioxide and water vapor in the air are the major 4 gases in the air. So it looks at the partial pressures. Yeah, so we're still messed up. It looks at the partial pressures of the different gases in air: nitrogen, which is the most, and then oxygen, carbon dioxide, and water. And also compares to when you breathe, inhaling and exhaling the air. So what happens when we inhale in terms of the air? Anybody know physiologically? Why do we breathe? What do we need from the air? That's important. Oxygen, right? So what happens to the oxygen when it gets into our lungs? Diffuses, yeah. It diffuses into the bloodstream. And then what happens?
We are oxygenated.
What?
We are oxygenated.
We are oxygenated. But like what happens in the cells? Why do they need oxygen? What do they do with it? Do we know physiology stuff? We took physiology yet? What?
The red blood cells carry the oxygen.
So they carry the oxygen to all around the body, and then what do the body's cells do with that oxygen when they get it?
HP.
Right, you do these various respiration reactions and use the oxygen. Oxygen gets reduced and forms carbon dioxide in the process of respiration. So what comes out then? Yeah, the carbon dioxide. Let's try this again. See if we have any luck. Oh, we might have it now. There we go. So most people think that you breathe in, and the oxygen that you breathe in gets converted to carbon dioxide and expelled. But that's not the whole story, actually, because here we go. This is the table I was looking for. The reason that's not the whole story is that if you look at this, it actually doesn't use up most of the oxygen that you inhale from air. So the oxygen that you take in is about 160 millimeters of mercury partial pressure. And then as it diffuses in through your lungs, you lose some of that oxygen. But then through the process of respiration, you expel that carbon dioxide. But you don't convert anywhere near to the entirety of the oxygen to carbon dioxide. So do you see that? The air you take in is 160 millimeters of mercury oxygen. The air inside your alveoli, like right at the point of respiration, has gone down to about 100 millimeters of mercury partial pressure of oxygen and increased the carbon dioxide pressure considerably. But you certainly haven't used up all the oxygen. So that's why things like, that's why you can breathe for somebody like assisted breathing and that kind of thing, because you haven't actually used up that much oxygen. Also interesting here, you can see that the carbon dioxide that actually gets expired, that you actually breathe out, is not all of the carbon dioxide that your body produces. A decent amount of it here gets dissolved into the blood and stays there, and that's what helps control the pH of your blood. When we talk about acids and bases, we'll talk about how carbon dioxide works to regulate the acidity of your blood and keep everything at the right level. And that's why when you hyperventilate, like when you breathe too much carbon dioxide out, you actually change the pH of your blood, and that's why you have negative effects from that. That's why you can pass out. So same thing like breathing into a paper bag. If somebody's like hyperventilating, it's because then you're kind of slowing it down and you're trying to stop all the carbon dioxide from getting out of your bloodstream because you need some of that in there. All right. So that's it. Questions? It's gases. So there's not really homework for chapter 6. Look through the book, look through some of the problems, but we're not doing all the math stuff that's in the book. So anything that says calculate the volume or calculate the pressure, calculate the temperature from this, we're not going to do that part. We're skipping over that. So we just want to know what those relationships are and how we can explain and justify those relationships using the kinetic molecular theory. Because there's not as much to do on this, use this time to go back and keep working on the homework from the last chapter, because that was a lot more difficult for a lot of people, that all the calculations and the setting up chemical equations and that kind of stuff. So make sure you're good with that before the exam in a couple weeks. All right, otherwise have a great weekend. I'll stick around if you have some questions. It will be probably through chapter 8. So beginning through chapter 8. Yeah.